Hi everyone. In the previous lectures, we started with the discussion of nonlinear amplifiers. Especially, we were treating nonlinearity in RF circuits. So we discussed several parameters to characterize a nonlinearity of an amplifier. We said, for example, when you talk about low frequency circuits, nonlinearity results. Example, when I say low frequency, especially speech processing circuits amplifiers used in speech processing. There, the specification of total harmonic distortion was very important. So what do we mean by that? So when I have a signal of frequency, say f1, when I pass this through a nonlinear system with a characteristic, it's not going to be linear as a function of the input. The output of this system actually will have frequencies in the multiples of, you will have frequency not only at f1, you will also have at 2f1, 3f1 and so on, at all the integral multiples of the input frequency f1. So this results in a poor quality output. I mean, your for example, an audio signal, the audio will not be an exact replica, just an exact amplified version of what the input was, but you will also start hearing some high pitch versions. Okay, so that's high frequency signals. So for that, we said in audio circuits, which is low frequency circuits, we used a parameter called total harmonic distortion. So we just compute all the powers of the, I'm going to call P2 as the second harmonic power, P3 as the third harmonic power, and so on, and then we add all the powers till the n harmonics, whatever number of harmonics present in the signal, divided by the total power. Okay, divided by the power of the first harmonic. So this gives you a metric. So and then we can either multiply it by 100 or take 10 log of this quantity, and express it as in decibels. Okay, so this is one metric also, or we can simply write it in terms of RMS quantities. So it will be 20 log of root of V2 square, V3 square and so on till Vn square by V1 square. So where V1, V2, V3 are RMS voltages. So they are actually RMS voltage, which is V peak by root 2. V peak of the first harmonic by the root 2. I mean, here I am saying Vi, Vpi is the peak voltage of the ith harmonic by root 2. And we said THD was a sufficient metric when we discussed low frequency circuits, but that's no longer the case when we talk about RF circuits, radio frequency circuits. Okay, so to characterize that, one of the first parameters we discussed was gain compression. We said that as you keep increasing the input signal, your gain starts to droop. And we also discussed about two important nonlinearity functions. How do you characterize an amplifier? We said we can model an amplifier as a compressive nonlinearity. So this model, it's a memoryless nonlinearity. Okay, so output just depends on the input. That it doesn't depend on the past or the present values. On the past values, such systems are called memoryless systems. And this model is a memoryless nonlinearity model. So the output actually, what we discussed was that the output will have a third harmonic component and also a first harmonic component. And we said that in this model as it is shown here, in this model, the gain will start reducing as you keep increasing the input signal. We discussed that the gain reaches a peak value and then it goes to 0. And what are these values? We discussed it in the last class. And mainly we wanted to find out the point where the gain reduces by 10% approximately. In fact, it was 11% of its nominal value. So, and we call that point as a 1 dB or 1 dB compression point. So we said that's the amplitude level at which the gain reduces by 11% of its nominal value. Okay, and we could also, A normally here represents the peak value of the sinusoid. So as we said, this is RF circuit, so the inputs will be applying mostly are sinusoids. We said that in radio frequency circuits, most signals will have very narrow bandwidth compared to their center frequency. So we can approximate this to an impulse concentrated at the carrier frequency. And here A represents the amplitude of that carrier frequency. So if I apply a signal of frequency A 1 dB to the system, the gain will be reduced by 11% of its nominal value. And we said that the A1 dB, the magnitude, is actually given by 0.145 into root of K1 by K3. I'm sorry, I think it is K1 by K3, because when K3 is 0, this function should be tend to infinity. The value of A1D should tend to infinity. And we also said we can represent this as P1 dB, which will be 10 log of, first you have to assume a 50 ohm system, then A1 dB square by 2 into 50, this normalized to 1 milliwatt. You can also express P1 dB in dBm. Okay, so but we need to know what is the resistance. I mean, here it's, I've assumed it's a 50 ohm resistance. Mostly it is normally, in most of the RF systems, it is a 50 ohm resistance. So that's a valid assumption to make. And towards the end of the lecture, in the last lecture, we also discussed about what we call interferer. So we said that in radio frequency circuits, especially, you just not only have your own signal, but you also have a very strong, sometimes very strong signal which you don't intend to receive. So for example, let's say I'll talk about GSM signals here. GSM is a standard, especially the second generation of phones, digital phones which they came into existence. They used to use what we call as GSM technology or the GSM standard. In that, the bandwidth of each user was given 200 kilohertz roughly of bandwidth per user, and there were many such channels, non-overlapping channels given to each user. Now say for example, from the tower you have a receiver here, which is your cell phone, and there is also another cell phone close by. Now what happens is that you are transmitting this signal. Your receiver is supposed to expect a signal, say at frequency f1 from the cell tower, and say the cell phone which is adjacent to you is transmitting at a frequency closer to your own frequency. So in fact, this is a wireless world, so wherein you can receive anything. I mean, you will start receiving any signal that's available in the air. Okay, so therefore you will receive both f1 and f2, and f2 can be very much stronger than your intended signal. And we discussed in the last lecture that in the presence of nonlinearity, what happens is that when you feed a signal, your desired signal at f1, and an unwanted signal at f2 which is very close to your signal, this can actually compress the gain of your system. Okay, it can compress the gain that f1 sees. See, so even though you might filter it out, your f1 itself at the output, you are supposed to get this, but you will actually be getting a reduced version of it. This is happening because of the presence of an unwanted signal f2 at it. This will not happen if there was no nonlinearity. This is mainly happening, the reduction in the gain is happening mainly because of the presence of, even though I put a filter after the amplifier, let's say I put a huge filter after the amplifier, but it have already reduced your gain. And we said that if the amplitude of this, the adjacent signal is very large, it can interfere with your signal, and therefore we called it as interferer. We also said if the amplitude is sufficiently large enough, then the gain for this will be nearly zero, meaning you will not receive any signal at all. So that's why it was also called blocker. So these are the different terminologies we used. One, we called it interferer. Okay, it's a single high frequency, high energy signal or high power signal which is very close to your desired frequency of interest. So such a signal we call it as an interferer. Now what does an interferer do? Normally if it was a linear system, it would not have done anything. But then because of the presence of nonlinearities, this interferer will start affecting the gain of your actual signal itself. And we said that if the gain is sufficient, for certain amplitude, if your amplitude of the signal is large enough, then it will start compressing the amplifier, and in fact it can even completely block your signal. So we took an example of k1x minus k3x cube, and we assumed x as a1 cos 2 pi f1t and plus a2 cos 2 pi f2t. And then we showed that the gain for, we are interested in the frequency f1, so we will get a term k1a1 minus k3 into the squared value of this, so which is a square by 2 3 into a1. Okay, so this was the value you will get. I'm just trying to compute what will be the coefficient of the term cos of 2 pi f1t. So now if you see, this a1 appears in this, a2 actually appears in the gain of the desired signal. So I can have some value of a2 wherein this function can actually go to 0. So when will that happen? When your k1 equals k3 into 3 into a2 square by 2. So if your a2 equals root of 2/3 k1 by k3. So for this value, if your a2's value is equal to this, then you will receive 0 signal at the output. Even though the amplifier has sufficient gain at that frequency f1, you will actually receive 0 signal, the gain becomes 0, or you will not receive any signal in your desired channel of interest. Okay, so this is called blocking. I mean, the signal completely blocks it, or receiver desensitization. Okay, so I'm just throwing in around words. So all these problems occur because of nonlinearity. So one is interferer, it interferes with your reception of your desired signal, or blocker, it can completely block your signal because of nonlinearity, and this happens because of gain saturation. Okay, so interferer and blocker, and then I used a word called gain desensitization. So your receiver, for example, all these problems occur mainly in the receiver. Your receiver is supposed to receive the signal very low levels. It should be very sensitive to the actual signal at frequency f1. But then because of the presence of f2, the gain becomes small, or I can say that the receiver is actually insensitive, or it's becoming less sensitive to your desired signal. So that's called gain desensitization. Okay, so these are the problems because of nonlinearity, and as we said, this can be a very severe problem in RF circuits. See, this doesn't happen in low frequency circuits because we don't have the concept of interferers. Okay, but a strong interference can actually saturate your amplifiers. So far in our discussion, we did discuss about interferers because interferers occur in wireless systems. I mean, you can't avoid them. Okay, that's one of the hallmark problems in I probably shouldn't have used the word hallmark, but one of the classic problems in RF circuits is the presence of interferers. Okay, now what happens if I have more than one interferer? So for example, at f2 and f3, so instead of, for example, your desired signal is at f1, but rather you have two interferers at f2 and f3. What is the effect of these two? Okay, so there is a more severe problem than a conventional single interferer system. So meaning we discussed a problem where there was one main signal and then there was an interferer which was very close to it. In fact, I forgot to mention in the last lecture, I also briefly mentioned a phenomenon called cross modulation. So if, for example, if I have a signal message M2 impressed onto the carrier F2 and message signal M1 impressed onto F1, when I pass this resultant two signals into a nonlinear system, a fraction of M2 modulation will start appearing on F1 and M1 will be transferred to M2 as well. And this happens especially in an amplitude modulated system. If I use amplitude modulation for modulating, this happens normally. If I use frequency modulation, this doesn't happen. So I think I'll solve one of the tutorial problems based on this, where we'll discuss about this problem of cross modulation. So this phenomenon is called cross modulation. Okay, yeah. So now I'm back to this problem of nonlinearity. Now we are discussing cases with two interferers, and this is very common in RF systems. Okay, so for example, I'll take the example Razavi gives itself, the textbook gives itself, is that he takes an example of a Bluetooth system. So Bluetooth, the channel spacing is around few megahertz. That's the channel spacing for Bluetooth. And you would have 2.41 gigahertz, 2.42 gigahertz and 2.4 gigahertz. So these are the different frequencies that I can have. Okay, so if you see that for a Bluetooth channel, so 2.41 and 2.42, if I have two signals very closely, I have more than a few Bluetooth devices surrounding me, now these two will act like interferers to me. Okay, now we'll see what is the effect of the two interferers. Instead of a single interferer, what will happen if I have two interferers? So what happens is that, let's say I have two interferers F1 and F2, I am feeding it to a nonlinear system. So I'll assume A1 is the amplitude here, A2 is the amplitude of this. So as we said, we can model them as two impulses of amplitude A1 and A2. Okay. Now F1 is this and F2 is this. Now if I pass this signal through a nonlinearity of this type, which is K1x minus K3x cube, this is the nonlinearity I am passing this signal through. We are interested, so I mean, if I just, we'll try to find what are the frequencies I'll get at the output of the system. So first term is K1x, so I'm going to obviously get F1 and F2. Okay, that will be multiplied by K1. Now this term, when I'm going to cube them, so I'm actually taking two signals. I'll write it as cos omega 1t plus A1 cos omega 1t plus A2 cos omega 2t, the whole cube of this into K3. Now if you look at this term, there is going to be a cube term, so that you will actually have the first term cube of that, second term cube of that. So you are going to have frequencies which are 3 omega 1, 3 omega 2. Okay, so then you'll also have 3a square b and 3ab square. These are the two terms you will have. Now 3a square b will be square of this and multiplied by this frequency as it is. So we will be generating frequency which will be like this, 2 omega 1 plus minus omega 2 and 2 omega 2 plus minus omega 1. Okay, as I said, when I cube this function, I'll also be getting omega 1 and omega 2. You know, omega cos cube theta can be written as cos 3 theta and theta, linear combination of that. It can be written in terms of that. And we saw that the first harmonic term, for example, K1 into A1 is the amplitude minus K3 into 3 by 4 into A1 cube. Okay, so this will be the okay, so this will be the expression for into cos omega 1t. So this will be the amplitude of omega 1. Okay, now we are interested in finding which of these components, for example omega 2, 3 omega 1, 3 omega 2 and these frequencies will affect your own signal or something adjacent to this. So for example, most RF systems are what we call as narrowband systems. Their band of operation is pretty narrow. Now say your desired signal is somewhere here, right side signal band, and two very close interferers are appearing here. Now I'll try to find out where does these different frequency terms come in. So first let's draw these two, which is your F1, or I'll just use F1 and F2. I've written in omega 1 and omega 2 there. So the harmonics, when I pass this through a nonlinearity, I'm going to get harmonics at, this will be far away, this will be at 3F1 and 3F2. That will be one harmonic. And then I'll also get frequencies at 2 omega 1 plus omega 2. So I mean that depends on the values of F1 and F2. So that will also be at much higher frequencies. I mean this will also, I'll get frequencies like 2F1 plus F2 and 2F2 plus F1. So I'll again get these two frequencies as well, which will be far away from F1 and F2. Now let's look at this term, which is 2F1 minus F2 and 2F2 minus F1. If you look at the first term, for example, I can write this as F1 plus or F1 minus of F2 minus F1. I'm going to call this term F2 minus F1 as delta F. So that's the difference between these two frequencies, which is delta F. Okay. Then the first term 2F1 minus F2 will occur here. So that is F1 minus delta F. The second term 2F2 minus F1 can be written as 2F2 minus F1, can be written as F2 plus F2 minus F1, which is F2 plus delta F. So that will occur at F2 plus delta F. Now if your delta F is very small, now you can see that these two harmonics, this term and this term, occur very close to your desired, the interference itself. Now if your signal is either here or here, then that's a problem for us. We are not only going to receive our signal but also components from two interferers. So this product is called intermodulation. Okay, and IM products, it's called intermodulation signal. So wherein two carriers which are very close to your desired signal of interest. So your desired signal can be F0. Now you can actually have two carriers F1, F2. They can actually, when they are fed to a nonlinear system, they can actually create a component at the frequency F0, which is say delta F away from this, and this separation is also delta F. Okay, so these two signals can intermodulate and create a component. So we'll see what is the magnitude of the components that we'll be receiving. Okay, so this is the nonlinearity I've assumed. I've assumed k1x minus k3x cube. This is the nonlinearity I've assumed here. Now if I feed the signal that I'm feeding to the system is a1 cos omega 1t. See, I am using omega 1 and f1 interchangeably, so I'm hoping there's not a confusion. So omega 1 is simply 2 pi times f1, and vice versa. Similarly omega 2 is simply 2 pi f2, and it will be a2 cos omega 2t. So this is the expression for x, the input signal that you are applying to the system. Now we will try to find out what will be the amplitude of the terms 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. Now understand, both these components will arise only because of this term. First term will not give that. So I will have minus k3 into a1 square 3a1 square a2. This term will be accompanied by 3a1 square a2 into cos square omega 1t into cos omega 2t. Okay, again this can be written as cos of 2 omega 1t minus 1 into cos omega 2t. Now the product of these two can be written as omega 1 plus and omega 1 minus, 2 omega 1 plus minus omega 2. So I'll get a term like this. So k3 3 a1 square a2 by 2 into cos of 2 omega 1 minus omega 2. So similarly we can show that the other term is going to be k3. I'll write the magnitude of it, the sign doesn't matter here. So it will be k3 or 3 k3 by 2 into a1 a2 square. Okay, so this is the term a1 a2 square into cos of 2 omega 2 minus omega 1. So these are the harmonic strings of these two terms. Now the first harmonic is obviously going to be approximately, I am going to approximate it to k1 a1 or k2 a2. Now these are the, this is again k1 a2. So if I plot the harmonics here, so this is at the output, I am going to feed these two signals at frequency f1 and f2 to the system. At the output, I have amplitude is a1 and a2 here. At the output, I am actually going to receive a signal whose amplitude is going to be k1 a1 and k1 a2, and the harmonic strings on either sides, this is going to be 3 by 2 k3 into a2 square a1 and 3 by 2, this will be a1 square a2 and 3 by 2 k3 into a1 a2 square. So this will be the harmonic strength of this. Okay. Now we'll also see what is the power of the signal that actually so I think I'll just I'll discuss it probably in the next lecture in more depth. So first, in this lecture I just wanted to introduce you to the concept of intermodulation products, and that happens when you have two carrier frequencies or two interferers which are very close to your desired signal. Okay, so they can, two interferers can actually generate components at frequencies very close to the if your desired channel is, for example, very close to two interfering signals, they can generate some noise or some unwanted components into our desired channel. Okay, so if I feed same amplitudes, if I actually feed same amplitude signals to both the amplifiers. In that case, okay, so if I feed A1 equal to A2, so we'll try to see what will be the amplitude that we'll be getting at the output. Okay, I just I just want to see if I made some small mistake in the equations. If I had two sinusoids, okay, okay, so there is a small it's just a small correction. So for example, it is cos 2 omega t. I missed a factor half here, so this should be 3/4. So that's what I was checking if the correction is fine. So it's 3/4, so it is 3/4 k3. I just wrote 3/2 so far. Okay, so yeah, so now the signal level that we will be receiving, or what I discussed right now, is if I have two interferers at f1 and f2, the signal that you will be receiving at your desired channel f0 can be computed. If you know the in the presence of nonlinearity k3, we can actually compute what fraction of it will appear here. Now if I feed two interferers of exactly same value, A and A, then the power that you will be receiving, or the amplitude you will be receiving because of intermodulation product, IM term, is going to be 3/4 k3 a cube, and this will also be 3/4 k3 a cube. Okay, so this is again an interesting result. So there is actually a way of expressing in terms of power. So for example, if I call this as P1 and this as P2, okay, we can actually show that the intermodulation product that comes here is actually proportional to P1 2/3 of P1 into 1/3 of P power 1/3 of P2 power 1/3. Okay, we can actually show, or I can write it as P1 square P2 whole power 1/3. So this is proportional to the power IM product term, or this term. Then the other side will be this. The power at this term, I'll solve a problem probably in the next class based on this. So on this side, the power here can actually be written as proportional to P1 P2 square whole power 1/3. Okay, that's a very trivially proven result. You can very easily show that result. So I'll probably discuss that in more detail in the next class. Okay, so yeah, so now what is the main goal of discussing all this is that in an RF system, we said we will not just have a single interferer. We saw that a single interferer was causing gain desensitization, or it can even completely block your signal. Now instead, I said if I have two interferers, these two interferers, of course they might also cause gain desensitization and all that, but they will also introduce a component at your signal of interest. Okay, this component is called IM, intermodulation component. Okay, or IM product, intermodulation product. Okay, and this is a very useful, that's why this test, what we normally do is that to test about nonlinearity of an RF system, we will feed two closely spaced tones. Okay, two tones which are very closely spaced, and then we will try to compute the IM products, the intermodulation products. Now if you look at the amplifier, I said assume that I am giving same amplitude A and A, two tone of same amplitude, then we know that the first harmonic strength is simply going to be K1 into A, right? It's just gain is K1, so you are going to get that. Now the intermodulation terms, if you look at it, the expression that we derived some time ago was actually 3/4 k3 a cube. Okay, so which means as I am increasing my amplitude, what will happen is that there will be one point when your signal, because if you look at the intermodulation terms, they are increasing proportional to a cube. See, k3 is constant, this is also a constant term. As I keep increasing a, the amplitude of the carrier which I am applying at the input, the interference I am applying at the input, the intermodulation terms will increase cubically. It increases much faster than the actual the main signals itself. Okay, and so we need a metric to tell you how bad the system is. How, in terms of nonlinearity, what will be the strength of intermodulation terms which I will be getting. If let's say I have two, as we discussed, why do we characterize parameters? Because usually it's easier to spec a system, or whenever I have two receivers I'm talking about, then if I have a parameter to compare the how good each receiver is compared to the other one. So we said in the last class we discussed something called 1 dB compression point, which was one metric which was useful in telling, especially characterizing harmonic distortion. As we increase the gain, as we increase the signal, amplitude was reducing, and also it also tells you about interference strengths and all that, as single interferers. Okay, but for example this one, when I have two interferers, okay, the strength that this signal will give rise to is not easily, A1 dB doesn't give a direct metric, it's not directly related to this. Okay, so we will need some other metric, especially for narrowband systems. See, compression point I can even define for low frequency amplifiers. Okay, but intermodulation is a phenomenon, it's mainly useful only in RF circuits. Now why is that? So RF circuits are mostly narrowband systems, very narrowband systems. So when you apply two carrier signals very closely into the band of interest, if let's say we are only interested in the harmonics, most of the harmonics will fall much outside the band of interest, and so they don't matter to us. But then the intermodulation components, or the IM components, will fall very closely within the band of interest, within the RF band. So that is why they matter a lot. So therefore we need a new metric which can tell me about the intermodulation terms. Okay, so that metric is what we call third intercept point, IP3. So we'll represent it as IP3, third intercept point. Now what is third intercept point? Mathematically, how do we define it? So as I said, if I apply two tones, so it's then third intercept point is normally measured using what we call as a two-tone test. We perform a two-tone test to a nonlinear amplifier. We'll feed two tones very closely spaced at say frequencies F1 and F2 with delta of difference and same amplitudes, and then we'll measure the tones of the intermod terms. The tones of both the intermod terms is going to be 3/4 K3 A cube, and the first harmonic term is actually going to be K1 into A. Okay, now we said when I apply an input, I'll call it IIP3. Okay, so this is called input third intercept point. Input third intercept point is nothing but we can define the nonlinearity in terms of the input amplitude you apply. When you apply this amplitude, the harmonic strength of the intermodulation terms will become equal to the main carriers, the main desired signal itself. Okay, so that parameter, it talks about how nonlinear your system is, So how do we calculate it? We just have to simply equate the first harmonic, which is K1A. So at K1 into A IIP3 must be equal to 3/4 K3 into A IIP3, the whole cube. So from this, if I find A IIP3, okay, so that will simply be root of 4/3 into K1 by K3. Okay, so this is your definition for AIP3. Also we can express, if you remember A1 dB, it was actually, of course it was much smaller than this. Okay, so in fact it was only 0.1 times this number, so it was something around 0.4145 into K1 by K3. So this was your A1 dB. Okay, so and also we can express AIP3, we can also express it in dB. So we can simply take 20 log of this quantity, root of 4/3 K1 by K3. Okay, or we can express it in terms of AIP3. Here this is a peak voltage, so this will be having units of volts, so this will be peak voltage. We can also multiply by 2 and then it becomes peak to peak voltage, or you can express it as power. So P IIP3 will be simply 10 log to base 10 of A IIP3 the whole square divided by 2 into 50. I'm assuming a 50 ohm system. This whole divided by 1 milliwatt. Okay. So you can also express PAIP3 in terms of dBm or as an amplitude level. Okay. So it is that level when your power, when your input signal, the intermodulation power becomes equal to the input signal itself. So normally, as we said, most engineering and RF applications, we normally always plot signals with respect to logarithms because it's easier to interpret the results. So for example, if I'm feeding a signal A in as an amplitude as a signal to the system, okay, the first harmonic strength or the signal which is proportional to this with the frequency will be simply K1. The intermod terms are 3 by 4 K3 into A in cube. So this is the intermod term. So now what I'm going to do is I'm going to take 20 log of both and plot it. Okay. So when I take 20 log, I'm going to get a graph like this, so which is 20 log of K1 plus 20 log of A in. So this is the logarithm of this. And similarly, this is going to be 20 log of 3 by 4 K3 plus 3 into 20 log of A in. So now if you look at this, these two are constant. This term and this term are constants. So I'll try to plot this. I'm going to plot 20 log of A in on this axis, and I'm trying to find 20 log of A out, okay, on this axis. So if you draw the first harmonic term, which is this term, the slope is going to be just 1, because the variable here is 20 log A out, the variable here is only A in, 20 log A in, the slope is going to be 1, right? In a logarithmic graph it is 1, in a linear graph it will be K1, but logarithmic graph it will be just 1. Now when I look at this guy here, I am plotting 20 log of A in, the slope here is it's actually 3 times more than this. So it will actually, if you look at this term here, this will be much smaller than this. So they both will start off at this term is going to be lower, so it will actually start off at a lower value, but it's going to raise much faster. Okay. So they both will meet at a point, and this will have a slope of 3. So this point where it meets, that point will be your 20 log of AIIP3. Okay, when the harmonic power or the amplitude of the signal, this is your third harmonic power. I am showing here as you increase your A in, it starts growing. Okay, the first guy, which is your main signal power, which is energy at frequency F1. Now this is actually power at frequency 2 F1 minus F2 and or 2 F2 minus F1. So these are the intermodulation terms. The power will raise 3 times compared to the first harmonic. Okay. So how do we measure this? How do we find AIIP3 in a simulation? How do we do that is we just feed 2 tones. Okay. And then we'll try to find this graph. We'll plot this graph of the first harmonic. We'll just measure the first harmonic, that is the harmonic strength of these two. We'll feed 2 equal amplitude signals. We will plot the graph. Okay. Now understand that as you keep increasing the gain, the amplitude also starts reducing. There will be gain saturation, right? We discussed this in the previous lectures. And similarly, we'll also monitor the third harmonic term. The third harmonic term is going to raise faster, but that is also going to saturate. Eventually nothing will go to infinity, because the amplifier is going to saturate and all that. So then what we'll do is we will extrapolate this graph, okay, and then find AIIP3. This is third intercept point, input third intercept point. So this is the first harmonic, this is the first term, which is amplitudes of F1 and F2. This is the amplitude of 2F1 plus 2F1 minus F2 and 2F2 minus F1. This is the intermodulation terms. Okay. What I am trying to tell you is that if you actually do it in a simulator and try to find AIIP3, these graphs will never intersect, because amplifier gains will start saturating even before you reach AIIP3. Okay. I'll just show you an interesting result here. So if I look at this equation here, which is the expression for IIP3, we can see that your IIP3 is definitely much greater than A1 dB. Right? I mean, this term is 1.333. So you should actually take root of 1.333 by 0.145. Okay, it's approximately root 10. So if I try to compute P approximately root 10, if I try to compute P IIP3, it will actually be 10 dB more than the 1 dB compression point. Approximately. This is an approximate result. So 4 by 3 is 1.333. So I'm approximating it as 1/10. I mean, if I multiply this by 10, I'll get this value. Okay. So PIIP3 is obviously much more than the 1 dB compression point power. So meaning your amplifier will experience compression even much before you apply IIP3. Okay. So which means your gain is going to reduce way before. I mean, way before IIP3, your gain will start saturating. It will start reducing. We know that 1 dB compression point occurs somewhere here. So this will be A1 dB. Okay, your gain is going to start to reduce way before IIP3. So then how do we actually measure IIP3? We just use mathematical simple extrapolation of this graph. Okay, but is there any more efficient way of doing it? Because what happens is when you're actually, let's say, how far should I run this graph? Those are the next points to worry about. Should I keep sweeping it for different gains? And so how accurate is this simulator? Because normally what happens is IIP3 will normally turn out to be greater than the supply voltage itself. Okay, so directly we can't measure it, and the other way is, one way is to extrapolate. Is there any simpler way of doing it? Actually, fortunately, there is a very simple way of computing IIP3 instead of extrapolating like this. Okay, so we'll just very easily we can do that. We'll see how to do that. Okay, I think I've said some points very fast. So what I'm trying to say is your IIP3 third intercept point normally is much greater than A1 dB. So what is A1 dB? It is that amplitude at which your gain reduces by approximately 11%. Okay, it's the compression point, gain compression point. So even before you apply IIP3, the gain starts reducing significantly. So you don't really, you can't directly measure IIP3. Okay, so you have to measure it using some other mechanism. So one is extrapolation. Now we are seeing, is there any simpler way of doing it? So fortunately there is. What we do is we first feed an amplitude signal AN, signal of amplitude AN, and then we get the first harmonic strength. Okay, I'll just plot it like this, or I'll use a different line. Okay, so this is AN, and I'll assume that AN is much less than even A1 dB. Okay, so that the amplifier is not compressed at all. And then I'll also find, at the same point, I'll also try to find what is the third intermodulation term. I'll try to find what is the IM term at the same frequency. Okay, the power of the intermodulation term. So when you run a simulation, two-tone test, you can easily find the for some small input signal level. Now let this power difference, the difference in two powers, be delta P. This level minus this level. Now we know that the gain of this guy is going to increase by 1, and this is going to increase with the slope of 3. So I'm now varying 20 log of A in, and I'm finding out 20 log of A out. Okay, the power of this is going to increase 3 times compared to this guy. Now I'll plot the difference between the two powers, I mean the difference between the two levels. I've called it as delta P here. Okay, so delta P here is nothing but 20 log of I'll call it A out. This is at omega 1 minus 20 log of A IM at output, the intermodulation term power at the output. So that's your delta P. Now it's the difference between this term minus this term. Now we know that this term increases with a slope of 1. This term increases with a slope of 3. So I'll try to plot delta P as a function of AN. So first at A in, the value of delta P, it's going to be delta P, it's the peak value. After that, the value of delta P is going to reduce, when I reach A IIP3, if you remember here, the two levels collide, they become same, so delta P will become 0. So delta P will fall with a slope of 2. That should be pretty obvious now. So because if you vary, this is simply some constant k1 times A in, and this is actually some constant times A in cube. So this will have a slope of 3, this will have a slope of 1. When I subtract the two signals, I am going to have a slope of 1 minus 3, which is minus 2. So your delta P will reduce like this. So this is AIIP3. Okay. So from this graph, I can easily compute what is the value of AIIP3, which is nothing but the slope of this line. So slope of this line is delta P divided by 20 log of AIIP3 minus 20 log of A in. Okay, A in is the point where you measured the signal that you applied. Okay, this should be equal to 2. Okay, the slope is delta y by delta x. Okay, so as you increase x, it's actually negative, it's actually minus 2, but this should be, actually it is minus 2. Let me write minus 2 here. Okay, y by x is minus 2. So if I apply this, if I take this term on this side, I'm actually going to get delta P by 2 equals 20 log A IIP3 minus 20 log A in. So your A IIP3 in decibels, okay, is simply going to be delta P by 2 plus 20 log of A in. Okay. No, I think I'll write it as, this is change in delta y. Okay, this is delta y by, so this is actually, I should write y1 minus y2. So this is actually 0 minus delta P. This should be equal to minus 2. So that's why the minus cancels out. Okay, I've just taken the, change in x by change in delta y by delta x is the slope, which is minus 2. So you will get plus here. Okay, so that's how the minus is removed here. So this is the expression for IIP3. Now if you see, all I did was, I just did one simulation at one single amplitude, and then from that I just calculated the power difference delta P log, just the difference of the two logarithms of the first harmonic term and the intermodulation term. With just the knowledge of this and this, I could easily calculate the IIP3. So this is a very, very useful approach. Especially especially for hand calculations, where somewhere you have to start your calculations. So this is a very useful simulation for that. A first cut analysis can be provided, first cut estimate of the nonlinearity can be provided by this result. Okay, so that's all about intermodulation. So this lecture I wanted to mainly discuss and introduce you to the idea of intermodulation. Okay, so what are the advantages of intermodulation? We said that why do we need a new parameter? Harmonic distortion, which 1 dB compression point told you about gain desensitization. It told you about single interferers. It told you what will happen if I have single interferers. Mainly 1 dB compression point tells you after a point when you can no longer use it as an amplifier, because your gain will start compressing out. But what happens if I have more than one interferer? Especially in a narrowband system, they can create havoc. They can actually create a new component at your desired signal. For that, we needed a metric. Okay, and we needed a new measure, and that we call it as AIIP3. Okay, again this can be expressed in volts or in dBm in power units. So for expressing it in dBm, we should tell you what is the resistance. I'll normally give you a 50 ohm system. If I say that, mostly this is true for wireless systems at least. Okay, so we can normalize it to 50 ohm and find the power. Okay, assume a 50 ohm resistor and then find the power dissipated and express the power in terms of dBm. Okay, so we found two important parameters, A 1 dB, which is the 1 dB compression point, or which tells you how much your gain reduces as you increase your amplitude. The next important point is IIP3, which talks about intermodulation terms. Okay, so if your IIP3 ideally should be very high. You know, for example, if there are intermodulation terms are very less, then it's good if the receiver is a good receiver. So for example, this is your gain alpha 1. If your if your K1 is much greater than K3, that tells you where you start from. You know, the initial value is determined by K1 and K2. Okay, because the gain is actually what? If you plot this 20 log K1 plus 20 log of A in, that is your amplitude. Okay, and the slope of this is 1. Now the other term, which is 20 log of 3 by 4 K3 plus 3 into 20 log of, so it's actually 60 log, I am just writing it as 3 into 20 log of A in. That this is the starting point. If this is very low, then it will start from a very low value. So it will start from here and eventually collide with it somewhere, you know. At IIP3, these two values will collide. So these two values will collide at IIP3. Okay, so this is a very this is what we discussed in today's lecture about what is the effect of nonlinearity, especially in RF systems. And IIP3 is a very useful metric because it is mainly applicable for RF systems because it's a narrowband. Whenever you have a narrowband system, if I have two signals, normally when you see low frequency circuits, you don't really care if your bandwidth is very small. Harmonics are going to fall way out of the bandwidth, so it shouldn't matter. But then in an RF system, it's very common that you will have two interferers which are very close by, and they can create an unwanted component at the center of your desired channel itself. Okay, and what is the strength of this carrier? I mean, this unwanted component at your desired channel, that is determined by the nonlinearity of your receiver, and that is characterized by IIP3. Okay, so if I have a bad receiver, then it's going to create a huge much bigger intermodulation term here, and that you can see by just looking at the value of IIP3. Your IIP3 will be very small in that case. If your IIP3 is very large, you are going to get much smaller intermodulation terms. Okay, so by looking at IIP3, you can say how good your receiver is. So this is about third order intermodulation. So probably in the next lecture I will talk about cascaded nonlinear system. What happens when I cascade more than one nonlinear systems, and in that case how do we characterize these parameters? Okay, so I will discuss that part in the next lecture. I'll stop at this point.